Oh, students, right here again today to get section 3.2, the gas laws. First key question, what causes gas pressure in a closed container? And our answer, collisions between particles of a gas in the walls of the container cause the pressure in a container of gas. And we have a definition for pressure, the result of a force distributed over an area. For example, the hockey puck to pressure. Moving hockey puck exerts pressure on an object that hits. A layer of shatterproof glass protects spectators. So the faster the puck is traveling, the greater the force of the puck on the glass. Greater force means more pressure. So when we go faster, we get a greater force and more pressure. And the smaller the area of the impact, the greater the pressure. If the edge of the puck hits the glass, it exerts more pressure than if the face hits the glass. When you got a bigger area, it spreads that force out over that big area, making a smaller pressure. Or SI, unit of pressure, derived from the SI units of force and area. Force is measured in newtons. Area is typically measured in square meters. So the SI unit for pressure, the Pascal, is newtons per square meter. Many times we often use kilopascals, and a kilopascals is 1,000 pascals. Kilo meaning 1,000. If you got a balloon filled with helium, there's more than 10 to the 22nd helium atoms in a small balloon. With all these helium atoms in, you're getting many particles colliding with the walls of the container at the same time, generating a measurable pressure. So even though each little atom is very, very, very small, and you have all these atoms hitting the sides of the balloon at the same time, it generates a pretty decent pressure. So the more frequent the collisions, the greater the pressure. And the speed of the particles and their mass also affect the pressure. So a number of things affecting pressure here. And that's our next key question. What factors affect gas pressures? And factors affecting the pressure of enclosed gas: temperature, volume, and number of particles. If we raise the temperature of a gas, we'll increase its pressure if the volume of the gas and the number of particles are constant. So temperature goes up, pressure goes up, as long as everything else stays the same. Very simple example of this, if you've ever seen an aerosol can tossed into a fire, as the aerosol can heats up, it causes the pressure to increase until that can explodes. Why they always say on aerosol cans and things of that nature, don't put them near a flame. Here, a firefighter is checking pressure on a tire using a pressure gauge. If they check that again after it's been out on the highway a long time, pressure is going to be higher. That's why if you check your pressure on tires on your car, you're always supposed to do it before you drive. Why it's cool. Because as a truck goes down the highway or a car goes down the highway, you get a lot of increase in pressure. It's illustrated on this slide. The motion of the tires on the highway heats up the tires and increases tire pressure. Got a lot of friction going on. There's that friction between the tires and the road generates heat. It causes the pressure to go up. And Y, as the temperature rises, the average kinetic energy of the particles in the air increases, causing these particles to move faster. And if they're moving faster, they collide more often with the walls of the tire. And if they're moving faster, they're hitting with greater force, and more collisions and greater force and causes the pressure to go up. And everything relating to pressure here is going to relate to the number of collisions. Reducing the volume of a gas increases the pressure if the temperature of the gas and the number of particles are constant. So, volume goes down, pressure goes up, as long as everything else stays the same. Nice illustration for this: if you have a cap on a plastic bottle, hold it, seal it back up, and you squeeze that bottle, you're causing the volume to decrease. And as that volume decreases, particles are going to collide more often. As you decrease the volume, particles are going to get closer together, which means they're going to collide more often. They're going to collide more often with the walls of the bottle and get more pressure. Another illustration of volume related to pressure, dealing with breathing. When we inhale, our volume is increasing. As we inhale, we make our chest cavity bigger. And this causes, once the volume gets bigger, the pressure is going to get smaller. And if the pressure is getting smaller, that allows a greater pressure outside to push air into our lungs. Then when we exhale, we're making the volume get smaller, making the pressure get bigger. Bigger pressure inside our lungs, less pressure outside causes the air to move out. Number of particles. Increasing the number of particles will increase the pressure if the temperature and volume are constant. So number of particles increases, causes the pressure to increase as long as everything else stays the same. When we got more particles, you're going to have more collisions and greater pressure. Okay. Everything based on collisions. Then there's some what we call gas laws relating these things in a quantitative manner. At this point here, we've been looking at just qualitative. As temperature goes up, pressure goes up. No numbers involved. And we're going to bring some numbers into it. We had this French physicist, Charles, collected some data on the relationship between the temperature and volumes of gases. And he graphed the data, as we're going to illustrate here. And he just got a temperature and a volume. Here we got a temperature of 0 degrees Celsius and a volume of a little under 7. And then we get a second point, and a third point, and a fourth point, and a fifth point, and a sixth point. So up to about 100 degrees, we got 9 point something for our volume. And that pretty much made a straight line. He connected them up. It is, it says over here, he extended the graph. And he extended it down till we got a volume of 0. And at the volume of 0, where it crossed the x-axis, he found the temperature would have been negative 273.15 degrees Celsius. And this is 0K on the Kelvin scale, and it's called absolute zero. So absolute zero, if it were possible, we call this an ideal gas, that as we keep lowering the temperature, the volume's going to decrease and decrease and decrease and decrease, and if it decreased enough, it would get to a volume of 0. That's absolute zero. The directly coldest temperature possible. And we developed Charles' law. States that the volume of a gas is directly proportional to the temperature in kelvins if the pressure and number of particles are kept constant. And we got this formula here, V1 over T1 equals V2 over T2. T1 and V1 represent temperature and volume before the change, and T1 and T2 after the change. Sometimes you might see this written instead of this way. You might see it V sub I over T sub I equals V sub F over T sub F. I and F standing for initial and final. Directly proportional up here, this means as one goes up, as temperature goes up, volume is going to go up. And we get that nice straight line on a directly proportional. Then we got a guy named Boyle. Describe relationship between pressure and volume of a gas. And we get what we're going to call an inverse relationship. And we'll see what that one looks like. Again, we plot some points. There's a second point. And a third point. And then we connect them and we get this nice curve. This is what an inverse relationship looks like. As the pressure goes down, the volume goes up. Bigger volume, lower pressure. Smaller volume, higher pressure. Increasing the pressure is going to decrease the volume. It squeezes the particles closer together. And get statement of Boyle's law. Volume of a gas is inversely proportional to its pressure if the temperature and number of particles are constant. And we write it as P1 V1 equals P2 V2. Then we get a thing we call combined gas law, which combines Boyle's law and Charles' law together. And we get P1 V1 over T1 equals P2 V2 over T2. And we'll look at a little example here. And we got a cylinder containing pressure of 100 kPa, volume of 75 liters. Pressure is then increased to 300 kPa. Temperature does not change. Find a new volume. So, get all of our information, which I just highlighted. And we got a P1, it's 100 kPa. P2, 300 kPa. V1, 0.75 liters. And let's look at what we're trying to find. In this case, V2. So we put it in the expression. P1 V1 over T1 equals P2 V2 over T2. We can cancel out the variable that does not change. So we just need P1 V1 equals P2 V2. We can rearrange that formula to V2 equals P1 V1 over P2. do a little substituting in, a little solving, and we get 0.25 liters. And is it reasonable? And volume should decrease as pressure increases. The pressure tripled from 100 to 300, and the volume 0.25 is 1/3 of the original volume, so it makes sense. Now, these we will do in class. So we'll come back to those later in class. We'll either already have done them, or we will do them depending on where our schedule ends up. But those will be in class work. Yeah, combined gas laws. Sometimes scientists will use balloons to do weather checks, call them weather balloons. Balloons filled with hydrogen or helium. It carries weather instruments up. So these are going to need to know a lot about pressure, volume, and temperature of the gases. And then a few quick questions. What causes the pressure to increase if more gas particles are added to collision? Remember, everything about pressure is related to number of collisions, so an increase in the number of collisions between the gas and the cylinder wall. Cause is always related to number of collisions. It's between the air, the gas, and the wall of the inside wall of the container. D, very close to the right answer, except they said the outside the container, so it doesn't make any sense. And the size of the particles do not change. And the volume of the container is not changing. Okay, when first blown up, a balloon is firm because of the air pressure inside it. After time, the balloon becomes soft as the air pressure inside drops. What could cause the air pressure to increase or to decrease? And they said, see, a decrease in the number of air particles as they leaked out of the balloon. Yeah. Things are going to leak out. And an increase in temperature would have caused the pressure to go up, not down, so that's why A didn't work. A decrease in the balloon's volume. If enough leaks out, the volume will decrease, but initially it's just going to be very firm to softer. And there is no chemical reaction going on here. 3, a gas has a volume of 15 liters and a temperature of 300 liters and an unknown initial pressure. Then the gas expands to 30, remains at 300 K and has a pressure of 300 kPa. What was the initial pressure of the gas? You might try this on your own. If you can pause the video here, try it, see if you can get the right answer. I'll work through it. Then you can check your answer. So if we're doing a problem like this, we always identify information. So we got a volume of 15 liters. I'm just going to say V is 15 liters. A temperature of 300 K. And an unknown initial pressure. So P equals question. Now these are all the initials, so I'm just going to call them V1, T1, P1. Then the gas expands to 30 liters. So the volume V2 is now 30 liters. It remains at 300 K, so that's also T2. And new pressure, P2, is 300 kPAs. So then our combined gas law says P1 V1 over T1 equals P2 V2 over T2, but our temperature never changes, so we can just get rid of that part of it. And we're trying to find P1, so we want to get rid of this V1, so we're going to divide both sides by V1, and then the V1s cancel, and we get P1 equals P2 V2 over V1. And I'm going to move up here top because I'm running out of room. So P1 equals, I'm going to put it in a little calculation chart, P2, which was 300 kPa, V2, 30 liters, over V1, 15 liters. Liters cancel. I'm going to go ahead and do the 15 goes into 30 twice. So all we got to do is take 2 times 300, and we get 600 kPa. If you got that right, that's excellent. If you didn't, we should have more practice. According to Charles' law, the relationship between the temperature and the volume of a gas is direct. Meaning as the temperature goes up, Charles' law, the temperature and volume of a gas, as temperature goes up, volume goes up, as long as everything else remains the same. When temperature of a gas in a closed container is increased, the pressure increases. Definitely true. As temperature goes up, pressure goes up. As I mentioned earlier, why an aerosol can would explode if you throw it in the fire. Okay, so that's our notes for section 3.2. And until next time, Mrs. Stripe.